Welcome to topic 9.4 and 9.5, Increases in the Greenhouse Gases and Global Climate Change. For as long as the Earth has existed, the climate has been changing. Nothing about Earth's climate is static. But what this video is going to explore is human-caused climate change. Climate change is more than just a single event or phenomenon, but rather a collective term that's used to describe a number of changes that are happening here on Earth. So when we're talking about climate change, it really refers to that anthropogenic, non-naturally occurring set of changes taking place. At its foundation, climate change is really the greenhouse effect that has been amplified by human activities. Those activities began with the Industrial Revolution in the middle of the 18th century and involved the combustion of fossil fuels, resulting in the accumulation of excessive greenhouse gases in the Earth's atmosphere. But in the last century, that excessive use of fossil fuels led to a sharp increase in the amount of greenhouse gases being released, and also the development of large-scale mechanized agriculture and the use of refrigerants like chlorofluorocarbons helped to contribute to those greenhouse gas emissions. There are a number of consequences as a result of greenhouse gases accumulating in the Earth's atmosphere. This video is going to explore some of those consequences, which include, of course, an increase in average global temperature, changes in precipitation patterns, the loss of the cooling effects of polar ice caps, changes in ocean chemistry and sea level rise, an increase in range for diseases, changes to soil chemistry, and sociopolitical consequences that result as people are displaced from their homes. But before we begin to explore anthropogenic climate change, we first need to take a look at how Earth's climate has changed historically over geologic time. Nothing about Earth's climate has ever been static. There is a cyclic nature to the cooling and warming of Earth's climate. In this graph, we can see climate patterns dating back over 500 million years and the resulting increases and decreases in Earth's average temperature. It may be tempting to look at data like these and use them to refute the evidence that supports anthropogenic climate change. There are a couple of important things to note, however, before attempting to do so. One of them has to do with the amount of time that elapses in between these warming and cooling cycles. If we go back about 300 million years, we find a point in Earth's history when the average global climate was cooler than it is now. The time it took for that cool period to experience change to a point where it became a warm period was on the scale of tens of millions of years, about 80 or 90 million years in the case of this cycle. Even in more recent times, we can see that these up and down warming and cooling cycles are taking place over tens of thousands of years. But if we zoom in on this last little period of time when humans are affecting global temperatures, we can see that the range of time that it's taken for these temperatures to increase is on the scale of decades, not centuries, not millennia, not millions of years, but a relatively quick period of time in Earth's history. We can also study temperature changes by looking at ice core samples. Ice core samples are produced by drilling into glaciers that have existed for tens of thousands of years, and then studying the composition of the air that's trapped inside of little frozen bubbles. We then can use those data to plot how changes in carbon dioxide and changes in temperature are correlated with one another. We can see that beginning with the Industrial Revolution in the 18th century and the increased combustion of fossil fuels in the 19th and 20th century, that it in fact correlates with a sharp increase in carbon dioxide accumulating in the atmosphere. The most immediate result in the increase of greenhouse gas concentrations is, of course, an increase in average global temperatures. Since the late 1800s, scientists have recorded, on average, that the Earth's temperature has risen by about 1 degree Celsius. While that may not seem like much, it doesn't take a lot of temperature change to have severe consequences on Earth's ecosystems. Most of this change has occurred, though, within the last 50 years. As the use of fossil fuels have increased, That results in an increase in carbon dioxide in the atmosphere and a resulting change in temperature. The Intergovernmental Panel on Climate Change, or IPCC, has stressed that it's important to keep average global temperatures from rising above 1.5 degrees Celsius to avoid the most severe consequences of climate change. Unfortunately, at the current rate of temperature rise, within the next few years, Earth's average global temperature will exceed that 1.5 degree benchmark. As atmospheric temperatures increase, there will be a number of consequences. One of the most obvious and perhaps most immediate ones is going to be a reduction in the amount of snow and ice found at Earth's poles, as well as a reduction in the size and extent of glaciers. But it's more than just temperature that's going to cause this to happen. We need to do a quick review of what albedo is. You might remember from an earlier unit that albedo is a measure of how reflective a surface is. Surfaces with relatively high albedo reflect more solar radiation than those surfaces that have a low albedo. So, the snow and ice that's primarily found at Earth's poles are responsible for reflecting a lot of solar radiation back out into space. As the snow and ice melts, that changes the albedo and therefore ends up causing an increase in the amount of solar radiation that's absorbed at those locations. Because of diminishing areas of relatively high albedo surfaces, more solar radiation is absorbed by sea and land, which ends up driving a positive feedback loop. Remember, positive feedback is not a measure of whether or not something is good or bad. Positive feedback simply means that the result of something happening amplifies that result so that more of it continues to happen. In other words, as snow melts because of warm temperatures in the atmosphere, the albedo decreases, which allows for even more temperature increases, which melts even more snow, which allows for even more temperature increases. Scientists measure the extent of polar ice at the North Pole, and we can observe the changes that have happened since 1979 relative to 2015. We measure the extent of sea ice during the summertime because it's typical that some sea ice melts, of course, when it's warmer, but the extent of ice loss is what's concerning to scientists. Although the melting of sea ice does little to affect sea levels, it does have an effect on ocean currents and ocean circulation. We're going to take a look at that a little bit later in the video. Right now, though, it's the concern about land-based ice melting that results in increases to sea level as that water runs off into the ocean. We can look to Greenland and Antarctica as good models for what we can expect to observe in the future. Every year, the ice on Greenland goes through natural freeze and thaw cycles. For some reason which scientists aren't fully understanding, in 2012 and 2019, there were extreme anomalies where more ice ended up melting than freezing during the winter time. As water runs off of Greenland, because it's land-based ice, that causes sea levels to rise. We can observe the same thing taking place in Antarctica. This visual here shows us some satellite imagery and shows us the extent of ice loss and the extent of ice gain. It's clear from data like these that there is more ice lost than ice being formed. We're going to watch a short video from BBC America that's going to talk a little bit more about Antarctica.
If we're thinking about what is sea level going to be like in 10 years, whether you're building a dike around your town or anticipating how far inland to move coastal cities in Florida, this glacier is a big piece of that question. And this is the location to be asking these questions at. We're standing right on it.
This is a historic moment. The first time anyone has tried to drill down through this glacier. Beneath the 600 meters of ice below me is the most important point of all, the point at which the ice meets the ocean water. This is IceFin. It's a NASA-funded robot submarine. This is the first time any measurements have been taken beneath what they call the Doomsday Glacier. It's the first time anyone has seen this. This is the point where the ice meets the warmer ocean water. It's the place where this huge glacier is rapidly melting.
So this glacier is significant because it is huge, and it's deep, it's thick. There's a giant volume of ice here. The bottom of the ice is below sea level, and so that means that it's very sensitive to change. So the ocean can very easily melt in and thin this glacier.
So Thwaites Glacier is really remote. It's right at the heart of the vast basin of ice that's West Antarctica. The glacier's the size of the UK. It's the stormiest part of the stormiest continent in the world, and more than 1,000 miles from the nearest research station. All this broken ice is almost 100 miles long. The ice rises almost a mile from the seabed, and it's collapsing into the sea at 2 miles a year. If Thwaites melts, it'll increase sea levels worldwide by ½ metre. But it sits in the middle of the West Antarctic ice sheet, and there's 3 metres more of sea level rise locked up in that.
Stand by. 3, 2. We have just detonated a shot and recorded the energy, the echo from the explosion, in order to map the grounding zone, so the point where the glacier glows afloat on the ocean. It is changing, it is migrating inland, and so this huge reservoir of ice behind us is becoming vulnerable to the ocean melting that's happening out there.
Let's be clear, the ice here isn't going to vanish overnight. It'll take decades, maybe even centuries for Thwaites to go. But as the work here has confirmed, it is melting increasingly rapidly, and that will mean huge changes for us all.
As sea level rise occurs, it threatens those species that rely on intertidal zones and other habitats that are close to the sea. Since the mid-1990s, sea levels have risen at the rate of about 3 millimeters or so per year, resulting in a total rise of about 1 meter. Sea levels have been rising, though, since the 1800s, but the most dramatic change has occurred in the last 30 or 40 years. The consequence for people is that those that live in low-lying and coastal areas will end up being displaced as water inundates the land that they live on. The loss of sea ice will have a negative impact on those species that rely on it for their survival. Species that use sea ice for migration, for hunting, or for brooding, raising their young, will be negatively impacted. As sea levels rise, though, and water begins to move farther inland, that's going to open up new habitats for some species to take advantage of. Having access to this new space could mean that certain species will actually experience population increases. But for other species, having deeper, darker water means that less light is going to penetrate into the water, and therefore there will be a reduction in photosynthetic output, and a reduction in those consumers that rely on those photosynthetic organisms. When the water rises, what would have been in the photic or lit up zone is now all of a sudden going to be in the aphotic zone if water levels rise too high. Earlier in the video, I said that sea ice melting doesn't really have an effect on ocean levels, and that's true. What it does have an effect on, though, is ocean currents. When we look at the surface of water and we see how wind interacts with it, it's really easy for us to understand how the wind can move water at the Earth's surface. So for that reason, for a long time, scientists incorrectly thought that there wasn't any movement of water beneath the ocean surface. In fact, there is an ocean current that travels around the globe in a conveyor belt-like system. This journey for the water takes about 1,000 years to complete, and the reason why this happens all has to do with wind at the surface and density. Warmer water from the equatorial region of the Earth is driven northward and southward to the poles by wind. As that warmer water is moved north and south, that water cools, becomes more dense, and sinks. Because of the sinking action, the convection of that water drives cooler water up at a different place on the Earth's oceans, bringing with it nutrient-rich water. Scientists aren't exactly sure how that upwelling of water occurs, but they have been able to track the movement of water all throughout the Earth's oceans. The red line on this diagram here indicates the warmer surface current, and the blue line represents the much deeper, colder water that's traveling close to the ocean floor. So what's the connection then to melting sea ice? Because those ocean currents rely not just on changes in temperature, but also on varying densities of water, when that sea ice melts, that releases a bunch of fresh water into salt water. Fresh water and salt water have different densities, and because of that introduction of that new fresh water, that can result in changes to ocean currents. Scientists aren't exactly sure how ocean currents can be affected, but British researchers were able to observe that circulation has already been slowed by about 30% since the middle of the 20th century. While it's impossible to predict exactly what kinds of changes ocean current alteration would result in, most models point to a dramatic shift in Europe's climate if that warmer ocean water being brought up from the South Atlantic and from the Caribbean is affected. Not only are ocean currents being affected, but so are air currents. We know that air moves north, south, east, and west. It rises and falls because of heating and cooling. You probably recall seeing a diagram something like this from earlier in the year when we were studying atmospheric circulation. The atmosphere is also a transport mechanism for moisture. And remember, all weather occurs in the atmosphere. So computer modeling suggests that there are going to be changes taking place to Earth's atmospheric circulation, especially the jet stream. The jet stream is a high-altitude, relatively fast-moving river of air. This computer modeling suggests that the jet stream will become more unstable and unpredictable as Earth's atmosphere warms. That also means that precipitation patterns are going to change as well. As that jet stream is carrying moisture around the globe, it's going to displace that precipitation in ways that we can't predict. This diagram right here shows the changes that may occur in precipitation amounts in the next century. The places that are shown in blue represent locations where an increase in precipitation is expected, and the places that are shown in orange and yellow are indicating decreases in precipitation. As precipitation becomes more available in some areas and less available in others, soil quality will be immediately affected by that change as well. Desertification is a process by which the soil, because of a lack of water, becomes less fertile. It ends up drying out and is no longer capable of supporting very much plant growth. It's one of the most concerning issues around precipitation pattern changes because as that land becomes less arable, the soil is no longer usable for farming. It's also more susceptible to erosion, which ends up increasing particulate matter in the atmosphere. This map here shows areas on Earth that are most susceptible to desertification. They're indicated with red and orange, and places that are less susceptible, which are indicated in green. Researchers for the European Union not only looked at desertification, but looked at a number of other environmental factors to determine whether or not there were compounding issues that would result in even more severe environmental changes. The places on this map that are showing in oranges and reds are the places that experience more of those coincident issues like desertification that will end up creating more severe environmental problems for the people that live there. Climate change is already affecting numerous species on Earth. We are no exception, but with increasing severity and frequency, climate change is likely to have more and more severe effects on us in the coming decades. People are going to be affected and more often displaced because of things like sea level rise. As waters rise and begin to encroach on low-lying and coastal areas, that's going to force people to move and migrate to higher ground. Additionally, as precipitation patterns are affected and some soils become drier and desertify, they're no longer useful for agricultural or farming purposes. That's going to force people to need to move to places where they can produce and grow their own food. Also, the availability of fresh water is going to drive people out of places that are lacking it and to places that have it. We don't know fully exactly how precipitation patterns will change, so it's difficult to predict where fresh water will still be available. Another factor are temperature changes. As global temperatures rise, it becomes more and more difficult for people to continue to live in places that are simply too hot to live in, or in places where people don't have access to air conditioning. You've probably seen in the news in recent years that the increasing frequency and severity of heat waves is resulting in a greater number of deaths. Also, an increase in the ranges of tropical diseases. Those tropical diseases would have been limited to those places that were warm and humid enough for them to survive. But as temperature increases are occurring and as precipitation patterns are shifting, that's opening up new habitats for pathogens and therefore results in an increase in infections. Unfortunately, the changes that are taking place are not going to affect all people equally. These changes are less likely to immediately affect more affluent societies, and most of the brunt of climate change is going to be felt by less affluent societies long before it affects those more rich nations. As a matter of fact, the Pentagon released a report in January of last year that described climate change as a national security issue. Unfortunately, this is probably going to lead to societal issues, political conflict, and who knows what else. Thank you for watching. That does it for this video. Until next time.